Hello and welcome to the ME452 final presentation where our product was the Philips hand blender. Here you can see some CAD views of our Philips hand blender product. And on this view, you can see the exploded CAD view detailing all 16 components of our product before redesign. We expect that the expected production volume of our product will be approximately 735,000 units per year. And we identified our primary and secondary customers as restaurants and home cooks and laboratories respectively. For our product analysis, we first did a fast analysis and identified two new branches of transmit energy and shred ingredients. For our first and second assembly sequence, we did a comparison to identify which was stronger, and assembly 1 ended up scoring higher than assembly 2. For our FCMM, we did notice that there were a few multiplicities for reinforced protection and reduced weight. This is an area we will try and redesign for. For our quad chart classification, we noticed something similar with a lot of products being in the low functional importance. So we will aim to reduce this number. For our product family design, obviously there will be different needs for primary and secondary customers, leading to these two different groups, the achieve textures and develop rotation. And this allowed us to identify the different platforms and modules we will need for our product. Some CAD for the primary and secondary customer modules include the primary tool, which would be used by both primary and secondary, and the potato masher and whisk attachment, which would most likely be used by primary customers. Some common interface include the tool interface and the motor interface, as shown here. For our product family assembly diagram, this is the original before redesign, but after redesign, we were able to take out a few nodes and reduce the product differentiation side.
For the design for manual assembly, we calculated the total assembly time of each of the parts of our hand blender, and analyzing these times and looking at the quad chart, we decided that the best idea we could came up with for the redesign would be to convert parts 10, 11, and 12 into one single part, and also make a redesign of the blade. The currently assembly efficiency before redesign is 19.30%. Here in the bottom, we can see that combining the two lower covers and the connecting ring will assure holding and also reinforce protection, but with one part instead of three. And with the redesign of the blade, we'll be able to achieve the same function, which is to achieve textures, but with a lower assembly cost and time. This is the design of the lower covers and the connecting ring before, which has a total assembly time of 13.58 seconds, and it has the following view in the CAD. After the redesign, we were able to reduce the part count and variety at the same time that we increase symmetry and add features to facilitate orientation and also features for easy insertion. The new assembly time is 3.95 seconds, which is 9.63 seconds faster. In relation to the product function, there are no important changes, but the manufacturing cost gets reduced as the manufacturing does not reflect great changes, but we're now only manufacturing one part instead of three. This is the design of the blade before the redesign, and it had an assembly time of 11.1 seconds. After the redesign, we were able to increase the symmetry of the blade at the same time that we're adding features to facilitate orientation and features also for easy insertion. As it happened with the lower covers on the connecting ring, there are no important changes in the product function, but the manufacturing cost also gets reduced as now the part presents a more rectangular shape and the bottom surface is now flat, which can be more easy to manufacture. And the new assembly time is 6.8 seconds, which is 4.3 seconds faster than at the beginning.
Assembly, we selected the assembly of the bottom. This was a good decision because the three parts had, as we see in the function companion matrix, very similar functions, so it was a strong choice to do a redesign of. Here we can see the assembly before doing the redesign, and the cost of the automated assembly was $3.8. There we can see it after, and we basically, for doing this redesign, follow the different DFAs. First, the increase symmetry. We increase symmetry all over the different parts. Then we add features to facilitate orientation during the assembly. Then we avoid tangling and nesting. And finally, we add features for insertion. Regarding the product function, it didn't change or had any important changes. And the manufacturing cost, it was reduced a little bit, but not big changes to have into account. We can see how the new redesign got us a final price of 1.8. That is a reduction of 52.4% from the previous redesign. Now I'm going to go through all the different parts as how we did the redesign of them. The spring, we just did a closed-ended in order to avoid that initial tangling. Here we can see the bottom, how we made two features in each side to make it symmetrical and help inserting with them. And the bottom cover, we did it symmetrical in order to help for the assembly.
Thank you. Now I'll take us into the process selection. First, we'll start with the blade, which the primary function is to achieve textures. Here we have the critical dimensions of the blade, and a standard sheet metal forming tolerance for holes is about 0.127 millimeters. Here we have the process selection chart. Based on the components in the chart, we've decided that sheet metal working and machining are both capable of manufacturing this stainless steel part. Here we have decided to go with sheet metal working. Next, we have the lower cover 1, lower cover 2, and connecting ring combination. We're connecting them in one part with the primary function to reinforce protection, reduce weight, and assure holding. Here we have that new part with the critical dimensions, and a standard injection molding tolerance is about 0.325 millimeters. Here we have the process selection table again, based on the same components in the table and the ABS plastic. We decided machining and injection molding are able to achieve the manufacturing of this new part. And again, we have decided to go with injection molding. Next, Jonathan will take you into design for manufacturing.
Here you can see one of the parts that we've selected to redesign for injection molding. Part 12 comes from the lower chassis and has a total part cost of 18 cents per part before the redesign. Parts 10 and 11, before the redesign, have a total part cost of 30 cents per part. Parts 10, 11, and 12 lack internal and external draft angles, which would make it difficult to injection mold, and there are some non-uniform wall thickness issues that contribute to a much longer cooling time than necessary. With our redesign, we've minimized the wall thickness where possible, added internal and external draft angles where necessary, avoided sharp corners in our design, and avoided side pulls wherever possible, thereby reducing the overall part cost. Comparing before and after the redesign, there's a significant cost savings, bringing it down from a total of 48 cents for the combined 3 parts manufactured individually to a new 25 cents per part for the combined part. We have eliminated the need for side pulls, thereby lowering the overall expenses involved in producing the part, along with reducing material cost and lowering overall operating expenses.
Before performing a DfM analysis of the part, we estimated the total cost to be $0.28. Due to the large amount of parts that we needed to be manufactured, the die costs become very small compared to the operating and material costs. Thus, we decided to identify ways to decrease the operating and material costs. We put the part into DfM Pro as well to see if there were any features that would fail and need to be modified, but nothing was shown. To decrease manufacturing costs, we flattened the longer blades to reduce the bending die cost, removed the hole to eliminate the piercing die, and made the longer portion of the blades more straight to increase the nestability of the part, lowering material cost. This reduced the overall cost to $0.202 per part. Plugging the part into hubs showed that the part before modification would cost approximately $0.14 and the after part would cost $0.13 using a power series analysis of 250, 500, and 1,000 part quotes. The difference between the before and after per the analytical method was 27.6% and the hubs analysis yielded 6.2%. We do not expect the blade to have any impact on functionality with these modifications, but the assembly cost may increase or decrease depending on whether or not welding is a more optimal method to attach it to the shaft.
For our product service system, we came up with a subscription-based module delivery service. As the products are used, the blades will begin to dull either when blending food or mixing chemicals. Instead of having to take apart the blender and manually sharpen the blades, customers could have sharp blades delivered when they are needed. The system could also be applied to other modules such as the whisk and potato masher, and customers can determine which products they like and how often they would like them. This would improve the customer experience as they'd be able to extend the lifetime of the product and wouldn't have to fix the product themselves. Additionally, the higher production quality of certain parts may even reduce the overall cost of the product slightly. This would also have positive environmental impacts as there would be less waste since the product will have a larger lifetime and therefore need to be replaced less. Overall, we identified some pretty strong benefits for our product through DFA and DFM. Through manual DFA, we were able to reduce the total assembly time by 16.78 seconds, and for automated assembly, we were able to save $2.02. Through DFM, we were able to reduce the part costs by 35.3 cents. Some pros of our design were high cost reduction, multiple modules for primary and secondary customers, and reduce the total number of parts. Some cons include the rack stand, which still has a high cost and low functionality, and the necessity to keep the product label, which is expensive and serves no function other than identifying it as a Philips brand hand blender. For our new approach, we would likely collect data from the product manufacturers to identify weaknesses within the product and target those for redesign. Additionally, we would interview primary and secondary customers to tailor custom modules to their needs.